Picture yourself standing in the middle of a massive steel suspension bridge. Like a convoy of heavy transport trucks just rumbles past you. And under your feet, the concrete and steel are vibrating.
Yeah, and it doesn't feel like a smooth, rhythmic hum,
Right,
right?
exactly. It feels terrifyingly chaotic. I mean, the cables are shuddering, the deck is bouncing.
The whole structure is just a blurry mess of movement.
Right. And if you wanted to understand what was actually happening to that steel, and you tried to describe that movement using traditional math, you would end up staring at a wall of calculus.
Vibrating structure in the real world, tracked moment by moment, it just refuses to cooperate. It's just too messy.
But there is a workaround, like a way to put on a different pair of mathematical glasses.
Yes. When you step out of the timeline and into the world of complex frequency response, that blurry, chaotic movement suddenly stops.
It completely freezes.
Exactly. The chaos transforms into a completely still, solvable, and honestly beautiful geometric landscape of structure impedance.
Trembling bridge.
The goal here is to really shift your entire perspective. We're going to look at how nasty, impossible calculus turns into a pretty straightforward algebraic tug of war.
Right. And we'll start small with just a single bouncing mass to find the hidden physical shapes inside its vibration. And finally, we'll scale up to see how completely different parallel systems, whether that's two pendulums tied together or massive electrical grids stretching across the country, actually talk to each other.
It's going to be a fun ride.
So let's start with that single bouncing mass. If we want to freeze the chaos of a moving object, we have to translate a time domain differential equation into a frequency domain algebraic one.
Right, and the absolute hero of this transformation is a very specific variable called the Fourier coefficient.
The notes just call it x sub n, right?
Yeah, x sub n. And this variable is really the key to this entire matrix-style view of the world.
How so?
Well, in the physical realm, you normally try to find the exact position of the mass as it wiggles up and down over time.
Which is a nightmare calculus part.
Exactly. But x sub n does something entirely different. It acts as a complex amplitude.
Okay, complex amplitude.
Yeah, it ignores the wiggling timeline and sits perfectly still, giving you two crucial, permanent pieces of information about the vibration. First, it gives you the magnitude.
And magnitude tells you the absolute maximum width of a vibration, right?
Yes.
So it tells you like the absolute furthest the bridge deck will bounce up or down.
Exactly. That's piece number one. The second piece of information it gives you is the phase.
Okay, I want to linger on this concept of phase for a second. Now, let's say I push a child on a swing. They don't always move forward the exact millisecond my hands touch their back.
Right, there's a slight delay.
Yeah, a delay between the driving force my hand's pushing and the object's actual response.
That's the phase, right?
That is the phase. It's the timing shift. And the brilliance of the math here is how we actually arrive at this simple answer.
The sources show that you can represent the actual wiggling movement as x sub n multiplied by a complex exponential term.
Yes, e to the power of in omega t. That complex term represents the continuous harmonic oscillation over time. And this is where the mathematical magic trick happens, right? Because we assume the vibration is settled into a steady, rhythmic wiggle. That complex time component factors out of the equation completely.
It just disappears.
You literally just divide it out and delete time from the universe.
It's incredibly satisfying. What you're left with is a surprisingly simple algebraic equation.
Okay, let's unpack this algebraic equation.
Yeah.
So the material's physical properties, its inertia, its damping, and its stiffness are all grouped together.
Right, they group together to multiply our hero variable, x sub n.
And they're fighting against the external driving force.
Exactly. It strips away the blur of motion. You are left with a raw structural impedance breakdown.
Which means you can clearly see how the internal properties of the object resist the outside force pushing on it at one specific frequency.
That's spot on.
Okay, so instead of calculating exactly where a mass is at every microsecond, I'm picturing x sub n as like a bouncer at a nightclub.
Oh, I like that. Go with it.
So the driving force is a massive crowd trying to push through the doors. But the bouncer doesn't care about tracking every single person's footsteps.
He's not doing calculus on the crowd.
Right. He just stands at the door, looks at the nightclub's internal stiffness and damping, weighs that against the crowd pushing inward, and delivers a final, flat verdict.
Basically saying, this is exactly how much the building is going to shake.
Exactly.
Yeah.
Is that the right way to think about it?
That mechanical intuition holds up perfectly. The bouncer hands you the final verdict of the fight.
Okay, cool.
But knowing the final width of the vibration doesn't tell us how that fight was actually won or lost.
Right. We just know the outcome.
To understand the mechanics of the brawl happening at the door, we have to look much closer at that phase delay.
The delay between the push and the movement.
Yes. And the source material emphasizes that we shouldn't view this delay merely as a few milliseconds of lag time. We need to visualize it as a physical spatial angle on a geometric wheel.
The phasor diagram.
Exactly. Engineers call it a phasor diagram.
I really love when math turns into physical shapes. Let's build this wheel. So if we are looking at this phasor diagram, we start with the simplest force, stiffness. Where does stiffness sit on our geometric wheel?
Stiffness is tied directly to displacement. Like how far you bend the beam determines how hard it snaps back.
Okay, makes sense.
So we place this at our baseline, 0 degrees, pointing straight forward to the right.
Okay, we have our baseline, pointing right. But a bridge isn't just stiff. It also has damping forces like internal friction that bleed off energy.
Right.
And damping is tied to velocity, which is the first derivative of displacement.
And the math here maps perfectly onto physical geometry. Every time you take a derivative in these equations, the math forces a 90-degree rotation on our wheel.
Wait, really? Every derivative is a 90-degree turn?
Yes. Since damping is tied to the first derivative, it rotates 90 degrees away from stiffness.
So it points straight up.
Exactly, pointing straight up the imaginary axis.
Okay, so stiffness is at 0 degrees pointing right, damping is at 90 degrees pointing up. Then we get to the heavy hitter inertia,
Inertia is tied to acceleration.
which is the second derivative of displacement,
Right, so taking a second derivative means we apply that 90-degree rotation twice.
meaning we rotate 180 degrees from our baseline.
You got it. So the inertia force points exactly opposite to the stiffness force, pointing straight to the left.
Wow. So they are locked in a direct 180-degree tug of war.
Precisely. We have our battlefield laid out.
Okay, so the driving force pushes the system, and depending on how fast that force is vibrating, the frequency, the system behaves in 3 entirely different ways based on this geometric tug of war.
Right, let's walk through the 3 regimes. The first is the low frequency or quasi-static regime.
Okay, low frequency.
Imagine you are pushing on the bridge very, very slowly. Because the movement is so gradual, velocity and acceleration are practically zero.
So that means the forces pointing at 90 degrees and 180 degrees damping and inertia, they barely exist.
Exactly. The driving force only has to fight the static stiffness of the material.
And since stiffness sits at 0 degrees, the driving force aligns perfectly with the movement. The phase delay is essentially 0.
Right, you push the beam and it moves forward instantly.
Okay, that's regime 1.
Then we speed up. We enter the second regime, which is resonance, the damping-controlled regime.
Resonance is where things get crazy.
Yeah. As your driving force vibrates faster, acceleration increases. That inertia vector, pointing backward at 180 degrees, starts to grow.
Because things are speeding up.
Right. It grows and grows until it exactly matches the length of the stiffness vector pointing forward at 0 degrees.
Wait. If inertia is pulling left with 100 pounds of force and stiffness is pulling right with 100 pounds of force,
They completely cancel each other out.
that's wild.
At resonance, the stiffness of the heavy steel beam and the massive weight of the steel beam effectively vanish from the equation.
So what is the driving force fighting against?
The driving force no longer has to fight them at all. It only has to fight the damping force, which is pointing straight up at 90 degrees.
So at resonance, your delay is exactly 90 degrees.
Yes, the force leads the movement by a quarter of a cycle.
That is insane. The mass just mathematically disappears.
It does, but what if we keep speeding up?
Right, regime 3.
We push the system incredibly fast and hit the high frequency or the mass-controlled regime.
And the sources say that at these blistering speeds, inertia completely overwhelms everything else.
Think about where inertia points on our diagram.
180 degrees,
Oh, yeah.
straight backwards.
Exactly.
The geometric wheel just keeps spinning.
It does.
But up until now, we have been living in a very isolated universe.
Very isolated. We've only analyzed a single bouncing mass.
Right, one swinging pendulum, one bridge column. What happens to this elegant math when you connect 2 moving things together?
This is where things get really dynamic. The notes describe this as a shift to coupled systems.
And apparently adding just one more mass completely shatters the isolation.
Mm.
Why does adding one more mass completely change the math?
The core difference lies in how energy is allowed to behave. A single mass on a spring is a closed conversation.
1 degree of freedom.
Exactly. It moves along a single axis. Energy enters, bounces between kinetic and potential, and slowly fades away.
But a coupled system, like 2 masses connected by a spring, is a network.
Right. They constantly pass energy back and forth.
The sources outline a beating phenomenon to describe this. Like, if you pull down on mass 1 and let it go, it bounces up and down.
But it doesn't just slowly come to a stop.
No. Its bouncing slowly shrinks, while, mysteriously, mass 2 starts to bounce harder and harder.
Mass 1 is bleeding its energy through the connecting spring directly into mass 2.
That is so cool.
It keeps doing this until mass 1 momentarily stops completely, having given away all its momentum.
And then the process reverses. Mass 2 starts bleeding energy back into mass 1.
They trade this motion in a rhythmic pulse, a beat.
Which means we are no longer looking at external phase, like the delay between me pushing the object and it moving.
No, the phase is now internal.
It's the architectural relationship between the 2 moving masses.
Exactly. You don't even need an external force to observe this phase. It is purely the relative alignment of the 2 masses as they dance with each other.
So if a single oscillator is someone pushing a child on a single swing, a coupled system is 2 swings tied together with a thick bungee cord.
That's a great analogy.
And the internal phase is simply whether the kids are swinging in perfect unison or whether they're, swinging in opposite directions and accidentally kicking each other.
Or stretching that bungee cord to its breaking point. Yes, that perfectly illustrates what physicists call normal modes.
Normal modes.
There are 2 fundamental ways this coupled system naturally wants to vibrate, and they correspond exactly to those 2 swinging scenarios.
Okay, let's look at the first one, the symmetric mode.
In the symmetric mode, the 2 masses move with a phase difference of 0 degrees.
So they're perfectly in phase.
Yes, like the swings, they move forward and backward together.
And because they are moving in perfect harmony, that bungee cord connecting them, the coupling spring, it doesn't stretch or compress at all.
It just sways back and forth with them. The connecting spring opposes no motion.
So it's basically doing no work.
Right, and because that central stiffness is effectively removed from the internal fight, the system behaves as if it has less overall stiffness.
And less stiffness results in a lower resonant frequency.
Exactly, it's a lower frequency mode.
But then we have the chaos of the antisymmetric mode.
Yes. Here, the 2 masses move with a phase difference of 180 degrees.
So they are completely out of phase.
Completely. When mass 1 moves right, mass 2 moves left.
The kids are swinging directly toward each other and then violently away from each other.
Right. And what happens to the bungee cord?
That bungee cord is getting stretched to its absolute maximum limit and then compressed inward.
This maximizes the deformation of the coupling spring. The spring adds all of its formidable resistance to the system,
And more stiffness drives the resonant frequency up.
which gives you a second, much higher frequency peak.
So a system with 2 masses naturally has 2 distinct frequencies. It's not just one anymore.
No, it splits into two.
Now, if you were listening to this and wondering how engineers actually track multiple moving parts at once without losing their minds, the notes bring in the matrices.
Yes. Matrix math.
If you haven't touched matrix calculus in years, don't panic. You don't need to do any scary math right now.
No, not at all. Just picture a grid or a spreadsheet.
A matrix is simply a highly efficient visual filing cabinet.
That's really all it is. In a coupled system, the position of one mass directly affects the force on the other. You have to track them simultaneously.
So engineers create a mass matrix and a stiffness matrix to organize all that crosstalk.
Exactly. And the layout of this stiffness spreadsheet is actually quite elegant.
The main diagonal cells represent the localized stiffness, right?
Yes. What a single mass would feel if you basically superglued the other one firmly to the wall.
But the real power lies in the off-diagonal cells.
Those off-diagonal terms represent the physical coupling. They mathematically quantify how motion in one location leaks a restoring force directly into another location.
By solving this spreadsheet, the math spits out two things: eigenvalues and eigenvectors.
It sounds intimidating, I know.
Yeah, but they are literally just the two frequencies we just talked about, right?
Yes, the eigenvalues are simply the two natural frequencies, the slow synchronous swinging and the fast opposite swinging.
And the eigenvectors?
The eigenvectors tell you the shape of the physical movement. They are literally the spatial manifestation of that 0-degree or 180-degree phase shift.
Okay, let's ground that. For the low frequency mode, the math produces an eigenvector of 1, 1, two positive ones.
Right.
Wait, does that just mathematically confirm they are doing the exact same thing?
Yes, they are moving in the exact same direction with the exact same amplitude. It is the raw mathematical manifestation of 0-degree phase.
Okay, and for the high frequency mode, the math spits out an eigenvector of positive 1 and negative 1. A 1 and a minus 1. How does a movement become negative?
Think about the direction on our wheel. That negative sign indicates it is moving backward.
Oh!
It is the math literally showing us that 180-degree phase delay.
The math perfectly paints the physical picture. That is amazing. And what absolutely fascinates me is how this geometric architecture applies far beyond bouncing springs and physical bridges.
It really does. It's universal.
Yeah, because the notes make a wild leap here. They state that this exact matrix framework scales up to describe massive electrical transmission lines.
Yes, large electrical grids.
But wait, how does bouncing masses apply to electricity? How does a bouncing mass describe invisible electricity?
Through mechanical electrical equivalence. The underlying physics are mathematically identical.
Okay, break that down for me.
In an electrical power line, physical mass is equivalent to electrical inductance. Physical stiffness is equivalent to electrical capacitance.
So an electrical grid is just a giant field of invisible springs and weights.
Exactly. When you look at parallel, three-phase power lines running side by side for hundreds of miles, they aren't isolated tubes of electricity.
They interact.
They do. The mutual inductance and capacitive coupling between those massive cables act exactly like our bungee cord.
Oh, wow. So if a massive power surge hits those lines, it doesn't just flow straight down the wire.
No, the interacting currents split. They form symmetric and antisymmetric modes, just like our bouncing masses.
Wait, really?
Yes. The power surge actually propagates down the cables at entirely different phase velocities, splitting into slower and faster waves based on how the lines couple with each other.
So the exact same geometric tug of war governing a child on a swing dictates the speed of a power surge rushing toward a city.
That is exactly what the math tells us.
That is mind-blowing.
Yeah.
Let's take a breath and recap the journey we've been on.
It's been a lot of ground covered.
Yeah. We started by looking at a chaotic, vibrating bridge, overwhelmed by the blur of time. But by utilizing complex variables like x sub n, we learned how to freeze time.
We factored out the wiggling, turning impossible calculus into clean, solvable algebra.
And we mapped those forces onto a phasor diagram, where we could visually watch stiffness, damping, and inertia fight each other across spatial angles of 0, 90, and 180 degrees.
We saw how inertia physically points backward, forcing massive objects to move left when pushed right at high frequencies.
And finally, we scaled up. We used matrix spreadsheets to file away the interacting forces of coupled networks, proving that whether you are tracking pendulums trading energy or power lines sharing an electrical surge, it all boils down to these fundamental geometries of phase.
It really shifts how you perceive energy transfer. You step out of the chaotic timeline, and you see the underlying geometric relationships holding the system together.